Welcome to the lecture on the course Descriptive Statistics with R software. From this lecture, we are going to start a new topic, and this is about movements. What are these movements and why do we need it? You may recall that up to now in the earlier lectures, we have considered two aspects of the data information. First is central tendency of the data, and second is the variation of the data. And we have developed different types of tools like as arithmetic mean, standard deviation, variance, and so on to quantify that information. Similar to this, there are some other aspects like as symmetry of the frequency curve, or how the values are concentrated in the entire frequency distribution. Similarly, there is another aspect, what is the hump of the frequency curve. So, in order to study all these things and some other important properties of a statistical tool, we need a concept which is called concept of movements. So, essentially you will see in this lecture that movements are some special type of mathematical functions, and using these movements we can quantify different types of information which is contained inside the data or the frequency table. So, let us first try to understand what are these movements. So, movements are essentially used to describe different types of characteristics of a frequency distribution, different features of a frequency distribution like as central tendency, dispersion, symmetry, peakedness, etc. Now, if you try to understand that how these things have been developed. So, if I try to see here, when I wanted to study the central tendency, then we defined arithmetic mean. And what we did? We had observations x1, x2 up to here xn. Then what we did? We just added them and we divided it by the number of observations, say here n. So, this gave us the information about the central tendency of the data, that where the mean or the average value of the data set lies in the frequency distribution or a frequency curve, right. Similarly, when we studied the variation in the data, we defined a quantity like variance or absolute deviation. I will try to show you both. What we did? In case of variance, we had the data x1, x2 up to here xn, and then what we did? We took the difference of these observations from their arithmetic mean, which we call as deviations. So, we took the deviations of each observation around the arithmetic mean. So, we obtain x1 minus x bar, x2 minus x bar up to here xn minus x bar, and after this we squared them. All the deviations were squared, and after this what we did? We simply took the arithmetic mean of these squared deviations. And similarly, when we computed the absolute deviations, then we had considered the observations x1, say here x2 up to here xn, and then and we wanted to study the absolute, say, mean deviation. Then what we did? We simply found the median of these observations and we took the deviation from their median like this, x2 minus x bar median and xn minus x bar median. And after this, what we did? We simply took the absolute value of these things. And after this, we just took the arithmetic mean of these values. Now you can see here what are we trying to do. In the case of arithmetic mean, we are trying to find out here 1 upon n, summation I goes from 1 to n xi. In the case of variance, we are trying to find out 1 upon n, summation I goes from 1 to n xi minus x bar whole square. And in the case of absolute deviation, we are trying to find out the arithmetic mean of the absolute deviations of xi from the median. So, now looking at these three examples, you can see here what are we trying to do. We are essentially trying to consider the deviations, say x1 minus some arbitrary value here a, the deviation of second observation from some arbitrary value here a, and deviation of the nth observation from some arbitrary value a. And then I am trying to use a suitable power function on this deviation. For example, if you try to look over here, please try to observe my pen. Here you are trying to use the square. So, I can make it more general. Instead of using here the square, I can replace it by here some general quantity, say here r. So, I try to consider now here the deviation of observation x1 minus a, x2 minus a, xn minus a, that is the deviations of observation around any arbitrary value a. A is, say, any value, any arbitrary value which we have to choose. So, now I try to take the rth power of these expressions and then I try to find out their average. This I can express as 1 upon n, summation I goes from 1 to n xi minus a raised to the power r. And now you can see that this function has several advantages. For example, if you try to take here r equal to 1 and a is equal to 0, you get here nothing but arithmetic mean x bar. If you take here r equal to 2 and a equal to, say here, x bar, then you get here variance of x. Similarly, if you try to choose other values, we can define some other functions which are going to represent the different characteristics of the frequency distribution. So, in general, I can call this function as, say, rth moment. And now you know that this is what I have defined for the data which is observed as x1, x2, xn, and that is ungrouped data. And if you want to define the same quantity for, say here, some group data, then this can be simply expressed into summation of fi I goes from 1 to k class intervals fi xi minus a raised to the power of here r and so on. So, now this is the basic idea behind defining a function which is called as movement. Now, what is the advantage of this thing? You will see here that when I try to take specific values of R and A, we get different types of characteristics. For example, when I choose R equal to 1 and A equal to 0, I get arithmetic mean, which is giving us the information on the central tendency of the data. Similarly, if I take R equal to 2 and A is equal to sample mean, then this quantity is giving us the information about the variation in the data. Similarly, we can think about that there are some other properties of the frequency curve like a symmetry or its hump of the curve, how to quantify those information. So, on a similar lines as these two values are going to give us the information on central tendency and variation in the data, so we can use the concept of movement to quantify the information about the symmetry of the frequency curve or the hump of the frequency curve. But in order to do so, first we need to understand the concept of movement and what are the basic definitions in grouped case, in ungrouped data case, and beside the idea which I have given you here, there are some other aspect. So, in this lecture I am going to consider about the raw movement and central movements, and in the next lecture I will try to show you how to compute them on the R software. So, in this lecture please try to understand the basic concepts, and they are going to help you in the further lectures and in future. Before going into the further details, let me specify my notation for grouped and ungrouped data. Now, I am going to consider two cases. Case 1, where the data is ungrouped and the variable x is discrete, and we have obtained n observations on x, which are denoted as small x1, small x2, small xn. Similarly, the second case is when we have the data which is grouped and we have a variable x, capital X, which is continuous in nature, and the data is obtained on x, and the same data has been tabulated in k class intervals in a frequency table like as here. First column of the frequency table is giving us the class intervals here like E1 to E2, E2 to E3 and so on. So, these are essentially your here k class intervals, and the second column is giving us the information on the midpoints of this class interval. So, they are denoted here as x1, x2, xk. So, x1 is going to give us the information on E1 plus E2 divided by 2 and so on, which is obtained from here. So, the second column is giving us the value of x1, x2, xk, but here x1, x2, xk are the midpoints. And similarly, in the third column we have the frequency data f1, f2, fk, which is denoting that the first interval E1 to E2 whose midpoint is x1 has frequency f1, E2 to E3 which is having the frequency f2 and so on, and the sum of all this frequency is denoted by here n. So, I can say here that the midpoints x1, x2, xk, they have got the frequency f1, f2, fk respectively. Now, after this I first try to define the movements about any arbitrary point here A. So, let me define here the general rth movement as we have just discussed. So, the rth movement of a variable x about any arbitrary point A based on the observation x1, x2, xn is defined as follows. For the case of ungrouped data, discrete data, this is simply the sum of the rth power of deviations, and these deviations are obtained, you can see here xi minus a, you can see here and then the arithmetic mean of these deviations has been obtained, and this is denoted as mu r prime. This symbol here I say mu r, and this symbol here, this is called here prime. So, this is the basic definition of the rth movement for the ungrouped data around any arbitrary point A. Now, similarly, if you have group data on a continuous variable, the same can be similarly defined, that now I am trying to find out the weighted mean of the rth power of the deviations, and the weights are given by the frequency, right, and this is also denoted as mu r prime, although I agree that these two, the mu r prime for the grouped and ungrouped data, they should have different type of notation, but we are using here same notation because at a time we are going to handle either the discrete case or the continuous case. So, this is how we try to define the rth movement of a continuous variable x around any arbitrary point A, and here this n is going to be the sum of all the frequencies. So, you can see here this is the same function that we have just developed. Now, I try to give you the idea of what is called here raw movements. Now, you will see that most of the things, they are simply the particular case of what we have obtained. So, as you had seen in the case of arithmetic mean, we are trying to take the mean of say x i's. So, similarly, instead of taking here x I, I am trying to take the rth power of x I, and this is going to give us the value of the rth movement, or this is called as the rth raw movement. So, if you try to see, this is nothing but in the earlier case, if you try to substitute A equal to 0, you get the same thing. So, the rth sample movement around the origin A is called as raw movement, and is defined here like this, in case the data is discrete. And similarly, in case if you have the group data on a continuous variable, the definition of discrete can be extended to continuous case, where you are simply trying to find out the average of the group data, say f I x I, and then you try to convert x I into x I raised to the power of here r, and here n is going to be the sum of all the frequencies. So, this is how we define the rth raw movement in case of continuous data. One thing you would like to notice here, that in the first line of the definition I am using here a word sample. You can see my here pen. Why I am trying to write down here the sample, and that is inside the bracket, what does this mean? Now, you can see here, I will try to explain this concept in this color, so you can notice it. Suppose I try to take the first case where I have defined the rth movement for the ungrouped data. You can see here that I am trying to take here the sum over the observed data. What does this mean? That I have taken a sample of data and I am trying to find out the average over the sample values. But if you try to see, there are two counterparts. One is the sample and another is the population. What is the sample? This is only a small fraction from the population. So, as we have computed this quantity on the basis of a sample, the similar quantity can be estimated for the entire population units. And essentially in statistics, we are interested in knowing the population value, but since this is unknown to us, so we try to take a sample and we try to work on the basis of sample. So, as we have defined the movements or say rth movement or raw movement or other types of movement that we are going to define, we are going to define on the basis of sample. But surely there exists a value in the population. So, the counterpart of the sample is the population, and when we try to compute the same movement on the basis of all the units in the population, that will be called as the population movement or the movement based on the population values. So, that will be defined here. For example, if I try to define this mu r prime for the population values, and suppose if I say that there are suppose capital N values in the population, then in this case this is going to be I goes from 1 to capital N instead of small n, and this value is going to be here x I raised to the power of here r. So, n is here the total number of units in the population. Now, there are two counterparts, one for the population and say another for the sample, but obviously our interest here is to compute the values on the basis of sample. So, in this lecture and in the next lecture, I will try to define these values, and you have to just be careful that whatever we are doing here, they are on the basis of sample. So, in practice we always do not call it as a sample movement, but we simply call it movement, but the interpretation is that the movements have been computed on the basis of given sample of data. So, this is what you always have to keep in mind. Okay. So, now we try to take a particular example of this raw movement, and I simply try to choose two values r equal to 1 and r equal to 2. And then in the case of ungrouped data, you can see here as soon as I say r equal to 1, I get this value mu 1 prime is equal to 1 upon n summation x I. And if you try to identify what is this, this is nothing but your arithmetic mean, and this mu 1 prime, this is called as first raw movement. And similarly, if you try to put r equal to 2, then I get here mu 2 prime is equal to 1 upon n summation I goes from 1 to n x I square. This quantity mu 2 prime is called as second raw movement. And if you try to recall where this quantity was occurring, you may recall that when you wrote the expression of variance of x, this was written as 1 upon n summation I goes from 1 to n x I minus x bar whole square, and which we have written as 1 upon n I goes from 1 to n x I square minus x bar square. So, you can see here that the first term here, this one, this is nothing but your second raw movement, and this quantity here x bar, this is simply the first raw movement. So, now this will give you an idea that why these raw movements are needed, and now you can see here that these raw movements are going to help us in defining the variance of x, right. So, in this case I can redefine the variance as say here mu 2 prime minus mu 1 prime say square. And similarly, if you try to take the grouped data, then when I substitute r equal to 1, I get here mu 1 prime, which is defined here like this, which is the arithmetic mean once again, and when I try to put r equal to 2, then I get mu 2 prime, which is here defined here like this. And this also has the same interpretation, that if you try to see variance of x bar, we had defined 1 upon n summation I goes from 1 to k f I x I minus x bar whole square, and we had denoted it yi goes from 1 to k f I x I square minus 1 upon n summation f I x I whole square I goes from 1 to k. So, this is nothing but your mu 2 prime minus mu 1 prime say square. Now, see here by this example that the interpretation and the utility of the movements in case of grouped and ungrouped data, this is similar, right. What you have to just observe here that if I try to choose here r equal to 0, then in this case this mu 0 prime becomes 1, and this is true for both the cases, for ungrouped data and for grouped data. Now, after discussing the concept of raw movement, let me define here what is called here as a central movements. So, we had discussed the rth movement around any arbitrary point say a x I minus summation of x I minus a raised to power here r. And in this case, if you simply try to choose a to be the sample mean x bar, then whatever is the movement that is called as central movement. So, the movements of a variable x about the arithmetic mean of the data, they are called as central movements. So, now if I want to define the rth central movement based on the sample data x 1, x 2, x n, then in the case of ungrouped data, I simply have to replace a by x bar. So, this quantity becomes here like this. So, if you try to see here, this quantity here is nothing but the rth power of deviations, and then arithmetic mean of this rth power of deviations has been taken. And this quantity is defined here as a mu r. There is no prime in this case. So, that is the standard notation, that the raw movements are defined by mu r prime and the central movements they are defined by mu r. So, the rth central movement in case of ungrouped data is given by this mu r is equal to 1 upon n summation I goes from 1 to n x I minus x bar raised to the power of r. And similar definition can also be extended to the case of group data. And in this case, this is the rth power of the deviation, and they are multiplied by the frequency f I, and then the arithmetic mean of these quantities have been taken, where n is equal to the sum of all frequencies. And what you have to just notice that in this case you are going to compute the arithmetic mean by this expression, that is 1 upon n summation I goes from 1 to k f I x I. And whereas in the case of discrete data, you try to compute the x bar simply as a summation x I upon n. So, this quantity is called as the rth central movement of a variable x. Now, let me try to choose here r equal to 1 and r equal to 2 and see what happens to the first and second central movements. So, first I try to take the case of ungrouped data. In this case, if I try to substitute r equal to 1, you can see here what I will get 1 upon n summation I goes from 1 to n say x I minus x bar raised to the power of here r, which is here 1. So, this is I can write down here summation x I goes from 1 to n minus say n upon n x bar. So, this quantity becomes here x bar minus x bar is equal to 0. Now, I can say that here that the first central movement in case of discrete data will always be equal to 0, and in the next slide I will show you that the same is true in the case of continuous data also. So, in general I can say that the first central movement is always 0. Similarly, when I try to substitute r equal to 2, then what I get here 1 upon n summation I goes from 1 to n x I minus x bar raised to the power of here r is equal to 2. Now, can you identify this thing? What is this thing? This is nothing but your sample variance, what we have defined in the earlier lectures. Now, I can say that the second central movement, which is denoted by mu2, is representing the variance or the sample variance. One thing I would where I would like to have your attention is the following. You can see here the second central movement is going to represent the variance, and first central movement is always 0, whereas the first raw movement, that was denoting the arithmetic mean. So, when you are trying to interpret these movements, you have to be careful while making an interpretation for the arithmetic mean. Arithmetic mean is represented by the first raw movement, and in the case of first central movement, this is simply denoting the sum or the averages of the deviation around mean, which is always 0. Now, in this step, I would also try to show you here that when I try to write down here this expression, then mu2 was written as here 1 upon n, summation I goes from 1 to n, xi minus x bar whole square, which was written as 1 upon n, summation I goes from 1 to n, xi square minus x bar square. So, I can write down here this quantity here, this is nothing but my mu2 prime, and this quantity here x bar square, this is mu1 prime square. So, mu2 becomes mu2 prime minus mu1 prime square. So, you can see here that this is a relationship between second central and second and first raw movements. So, what I am trying to explain you here, I am trying to show you here that there exists a relationship between the central and raw movements. I have shown you here that how to express the second central movement as a function of raw movements, and I have taken here the example of r equal to 2. Similarly, if you try to take r equal to 3, r equal to 4 and so on, then you can obtain a similar type of relationship between central and raw movement. One more important aspect which arises here is the following. Usually you will see that in statistics we are considering the first, second, third and fourth movements, either they are raw movements or the central movements. Well, one can very easily compute the higher order movements, say fifth, sixth and so on. But up to now, what has happened that we have the interpretation for the first 4 movements. For example, first movement, that is the first raw movement, that is indicating the value of, or the, it is quantifying the information of central tendency of the data. Second central movement is giving us the information on variability. Similarly, I will try to show you in the forthcoming lectures that third movement is giving us the information on the symmetry of the frequency curve, that is called as property of skewness. And similarly, the fourth movement will give us the information about the hump of the frequency curve, the peakedness of the frequency curve, and that property is called as kurtosis. But what is indicated by fifth movement, sixth movement and so on, that is still an open question. So, that is the reason that usually we are interested in finding out the movements up to order 4. There also exists a clear-cut relationship between rth central moments as a function of raw moments. But here I am not showing you here, I am not discussing it here, but I will request you please try to have a look in the books, and there it is clearly mentioned. But here I would certainly show you that what is the relationship of first 4 central movements with respect to the raw movements. Now, if I try to take the r equal to 1 and r equal to 2 in case of continuous data, group data, then we have the simple similar interpretations, that in the case of first central movement, this is going to be fi xi minus x bar, I goes from 1 to n. So, this is here 1 upon n summation I goes from 1 to n fi xi minus say here x bar. So, you can see here this is nothing but x bar minus x bar is equal to 0. So, once again I have shown you that the first central movement in case of continuous data is always 0. And similarly, if you substitute here r equal to 2, then this quantity is nothing but the sample variance. And in this case also, this mu 2 can be represented as mu 2 prime minus mu 1 prime say square. So, this is again the same outcome that we have obtained in the case of ungrouped data. So, you can see here and notice that this relationship is not going to change in the case of grouped and ungrouped data. Now, if I try to choose here r equal to 0, then I will always get mu 0 equal to 1. Either we have an ungrouped data or a group data set. Now, after this I will show you what is the relationship between central movements and raw movements. You have observed that the first central movement and first raw movement both are taking the value 1, and first central movement here, this is taking the value always 0. These are the 2 points where you have to be careful. I already have shown you this result, where I have shown you how I can express the second central movement mu 2 as a function of first raw movement and second raw movement. Just using a similar concept, I can also express the third and fourth central movements as a function of raw movements as a function of mu 1 prime, mu 2 prime and mu 3 prime. And similarly, the fourth central movement can be represented as a function of mu 1 prime, mu 2 prime, mu 3 prime and mu 4 prime. And you may recall that mu 3 prime is nothing but 1 upon n summation I goes from 1 to n xi cube, and mu 4 prime is, which is the fourth raw movement, I goes from 1 to n summation and then xi raised to the power of here 4. So, you can see here that these are the relationship of central movement and raw movements. Well, I am trying to give you here only 4 relationship as I said, but using the binomial expansion you can obtain a general relationship between the rth central movement as a function of the first r raw movements, and that is available in all the standard statistics books. So, I will not do it here, but I would like to stop here. I have given you the basic concepts of movements. Well, this lecture was purely theoretical, but we also know that any development is based on the theoretical construct. Unless and until you understand the basic fundamental, you will not be able to understand what the software is trying to do. And these are very important concepts in the subject statistics. So, that was my objective, to give you an exposure of this concept. Now, in the next lecture I will try to consider the concept of absolute movements, and I will try to show you that how these movements can be computed on the basis of R software. And after that, I will introduce the concept of skewness and kurtosis. So please, you take a break, revise the lecture, try to read from the books, and I will see you in the next lecture. Till then, goodbye.